Hello and welcome to today's webinar on Enhancing Productivity in Automated Machine Tending, hosted by NTMA's technology team. My name is Mike Hirsch. I am NTMA's tech team leader, and I'm honored to be your MC today. The technology team's mission is to provide accurate and timely information on current and emerging technologies that can improve your bottom line, your productivity, your competitiveness, and quality. One of the ways we do this is by hosting relevant technology webinars. The topics we choose come from you, our membership. So if you'd like us to cover a topic that's important to you, just shoot us an email, pick up the phone, or type us a note in the chat box. We value your time and promise to end on time as well. If you haven't already done so, please enter the audio PIN number that you received as you signed in. The format is pound, PIN number, and pound. This will help us provide the highest quality webinar for all who are attending. In today's webinar, our friends from FANUC America and SCHUNK will discuss the use of both robotic automation and specialty workholding systems to enhance productivity in automated machine tending. FANUC will be discussing ways to via robots that are specifically targeted at automated machine tending. VERO-s handle payloads of 4 kilograms to 2,300 kilograms. That's roughly 9 pounds to 5,000 pounds. Additionally, FANUC will discuss software products that play a key role in the seamless connection of the robot to the machine tool. SCHUNK will discuss the use of its innovative VERO-s workholding system. VERO-s is a modular quick-change pallet system for very fast and extremely precise resetting of workpieces, clamping devices, and other equipment on 3, 4, or 5-axis machining centers. We are honored to have 2 presenters on hand today. The first is Jeff Dawson from FANUC America Corporation. Jeff has been with FANUC for 21 years, and in his current role, he works with machine tool builders, automation integrators, and end users of machine tending and material handling applications. We're also joined by Brad Evans from SCHUNK. Brad has been involved in our industry for over 20 years. The last 10, he's been the stationary workholding product manager with SCHUNK. If you'd like to ask questions, please use the chat box function on the GoToMeeting screen, and be sure to send all. Our presenters will answer them either during the Q&A or at the end, whichever is more appropriate. If you joined us late and haven't already done so, please enter the audio PIN number that you received as you signed in. Again, the format is pound, PIN number, and pound. This will help us eliminate audio distractions. So without further delay, Jeff Dawson and Brad Evans on enhancing productivity in the automated machine tending. Jeff and Brad, thanks in advance for educating us.
Thanks, Mike. Jeff Dawson here from FANUC, and would like to talk a little bit about automated machine tending and how to help increase your productivity. Thanks for allowing us to be here today. First, I'd like to start out and talk about why companies should automate machine tools. There's the obvious operator efficiency and increased productivity and spindle utilization. These are kind of the obvious above the water parts of the iceberg. But below the water, there's some other benefits that are not as easily seen. Things like reducing your operation costs, increasing employee satisfaction by removing them from what we call the 3Ds, the dull, dirty, and dangerous environment. Adding secondary operations to a robot cell. So not only doing the machine tending, but other processes that are part of that. I'll talk about that a little bit later. Improving the ergonomic and safety aspects of an operation. There's the ability to increase quality. There's less handling of the parts, more passing the parts between processes, and the ability to add inspections to increase that quality. There's the ability, sometimes we were able to eliminate some costly conveying and fixturing through the use of bringing parts in a storage type system, which Brad will talk about the SCHUNK VERO-s later, which helps out there, or even just bringing in baskets of parts, which we'll talk about. There's the reduction of CapEx and floor space, and the ability to run a lights out operation. Just a little bit about robots. As Mike mentioned, we have robots of all sizes and types, ranging anywhere from even down as low as a half a kilogram for some of our pick and place. But when we're looking at machine tending, we're really looking at the 4 kilogram to the 2,300 kg world's largest robot. All the robots have the ability to be guided with vision. This is a built-in capability, so we can give the robot sight in order to find parts and do other processes. And robots are going to be one of the most reliable pieces of equipment, if not the most reliable in a factory. Mean time between failures is greater than 100,000 hours, pushing greater than 120,000 hours these days. We talk about automation cells in general. They're scalable, so depending on part sizes, the same general cell will be applicable to small parts. So you can see in the upper left corner a small turning center with a small robot conveyors, up to, down in the lower right corner, something very large with a large machining center and larger parts. But in general, both cells operate the same. Same programming, same software, same general controls, same interfaces. You can also look at the scalability of robotic cells from the very entry level to the complex. So start at a very entry level, simple pick and place, loading a machine tool can be at the low end. As you start adding things like fixturing or flexible feeding, vision, larger robots, different systems, up to the point where you talk about plant monitoring systems and plant IT involved, things like factory talk systems, and everywhere in between, multiple robot systems. So it's really a scalable technology where you can get in at the entry level up to a very complex manufacturing floor. Talk a little bit about how these can be configured. Really 4 basic configurations of machine tending. There's the robot inside the machine tool, side load, front load, and top load. We have some follow-up slides beyond this to talk about each of those setups. So when we talk about a robot in a machine tool, the compact robots like our 4 and 7 kg LR mate fit well inside a machine tool. And these are typically, these are IP67, so they are able to take some liquids, some sprays. But when the environment is much, when there's a lot more coolant, a lot more moisture in the machine, we do have a form of that robot that is waterproof and can handle an 1800 PSI spray. So we call that a washproof robot. So good configuration. Typically, we'll see that a lot in grinder type cells and small machining cells. Side load of the machine. This allows you to keep the front of the machine open, so keeps that floor space open, keeps access for the operator. At times, this type setup will be used for what we call hybrid machining, where during the day that machine is accessible from the front for the operator to load parts in, maybe smaller batches. At night, a conveyor system or a drawer system or some other part delivery system can be set up to run a batch of parts, so basically a lights out operation. So a very efficient usage of automation and usage of floor space and layout. When we're looking at a front load, sometimes there's always been a detractor that putting a robot in front means the machine is blocked. There is a configuration or some configurations here where the robot can be angle mounted or even wall mounted so that it can be parked out of the way to allow the operator full access to the machine for changing fixturing, changing tooling, and other maintenance and operational type activities. Then as we get into some larger machines and maybe machining lines, a top load system comes into play. A lot of times in the past this has been through the moonroof with a linear gantry type setup, but they can only load through the front. If you go with an articulated robot on a gantry, either what we call an overslung there in the lower right or a side slung there in the lower left, these can go in through the top of the machine through the moonroof, or they can also access through the front of the machine as well. So this will allow the savings of floor space, getting the robot up and out of the way, allows the operator access to the front of the machine, but also is quite flexible and allows you to handle multiple machines with one arm, depending on when the cycle times allow. It's also what we call pre-engineered solutions, and these pre-engineered solutions are standard off-the-shelf robot loading systems that several of our integrators and machine builders have developed that are conducive to small, high-mix, low-volume type setups, like a drawer cell in the lower left. You can have 3 or 4 different drawers loaded up with parts of different sizes and run those in batches. So run the small parts in the top drawer, then if you need to change over to another size, it's all the work pieces are loaded up and ready to go. On the right side, you see some kind of storage and retrieval type systems, and these are very another off the shelf, and these are very conducive to a palletized system like the SCHUNK'S VERO-s that Brad is going to talk about a little later. Vision is a good usage of a good addition to a robot. Vision basically gives the robot sight. It's a scalable product, so anything from a calibration to error-proofing. Error-proofing would be inspection. That would be a version of inspection, using the robot to inspect parts, measure parts, using that camera that's built into the robot. We use the robot to guide, or we use the camera to guide the robot. We can do what we call visual tracking, and then we have the ability to find parts in 3D space. So where does the 3D space come into play? Instead of having to take parts out of a bin, load them onto a conveyor in an organized fashion for the robot, you can present the robot with a bin or a tote of parts and use that 3D vision technology, which finds what we call a 3D point cloud, is able to locate those parts and pick them out of these type delivery systems to the robot. So saves a lot of additional labor that is normally associated with moving those parts out of the bins and onto another system that can be loaded by a robot. Talk a little bit about floor space savings and some safety here. There's collaborative robots are a real buzzword these days, and there are 2 types of collaborative setups predominantly, and both are used to provide additional access to the machines or the robot cell while not limiting production or uptime in a system. The first is what we call speed and separation monitoring. So this takes a standard robot, and in the video you'll see the robot is running full speed, no fence around the robot. You see the safety, what we call safety scanners attached to the side of the machine. You'll see the operator approach the machine from the left here, and as they get into the safety zone, the robot will slow down to a safe speed. The operator at this point still cannot touch the robot, and the robot continues to run, but the operator may be inspecting something. If they need to get closer to maybe access the control panel on the robot or on the machine tool, the robot will stop safely, and as they exit the cell, the robot will begin running again. So it saves a lot of operator interaction as far as having to start, stop, open gates, and so on and so forth. A second version of collaborative robot is what we call power and force limited collaborative robots. So these robots will allow to be run without any safety guarding or safety sensors around them. When they run in that mode, they run about at that safe speed of about 250 millimeters a second. But what happens is if the robot touches an operator or the operator touches the robot will stop safely and then continue on once cleared. In this case, these can also run a little bit faster. In this case, we would look at this robot in this video. It would have a safety scanner. It's running full speed for this robot. It's doing a part exchange on the table there. The operator wants to come in and inspect that part. You can see the robot slows down to a safer speed while continuing to run. So now it's in that 250 millimeters a second contact stop speed. Can continue to move next to the robot or next to the operator while the operator makes changes to the panel. And then as the operator leaves the area, the robot goes back into full speed. So again, this gets rid of some of the barriers regarding access to a panel and access to the system. Connecting robots to CNCs. There is a traditional way of doing that, which tends to be a little bit custom, but it allows a little bit more integrator-defined content. And this typically comes in when there are multiple machines or maybe some additional processes and machines. But these do tend to be a little bit of additional cost. When we look at the other way is what we call machine tool easy connection. This is a connection between a robot and a machine tool. It allows access to the robot from the machine tool panel and to the machine tool from the robot panel. So the benefit here is floor space is at a premium, and the robot has to, and you don't have a machine where the control panel can be located outside of the cell. You can actually access the robot's teach pendant to make CNC adjustments and CNC offsets and look at CNC statuses. Vice versa, if for some reason the CNC operator panel is more accessible and the robot control panel is not, you can access robot statuses and robot screens from the CNC panel. We take this a step further, and when we look at our PC-based CNC front end, we can actually do what we call teach pendant on HMI, which allows us to actually have full access to the robot, including jogging from a CNC panel. So again, we can get rid of the robot teach pendant, have full control of the system from one point of control on a CNC panel. This can be done through various Ethernet protocols, including Ethernet IP, FANUC IO link, CC link, and other protocols. So we cover the gamut as far as various machine tools that we can talk to. Even can do this on the iPad, as it's shown in the upper space there. So wanted to finish kind of with a little video here that kind of demonstrates some of that technology that we just reviewed. So we're really showing here a part that's going to be showing how the robots, or how parts that we're handling and are being machined are coming out of in an automobile or are being done automatically. So in this case, there's a bin of parts. So we would use the 3D vision to find those parts in the bin. Load the machine, unload the machine, and load the second machine. So here's the integration is through easy connection here, robot through an Ethernet switch to the machine or multiple machines. You see in here the operator has control of the robot, or able to access the machine tool from the robot teach pendant screen. They can check CNC status, make offset, and the other operator has the ability to do the same thing, where they can actually access the robot from the CNC screens. In this case, at any one time, only one single point of control would be implemented. We also have the ability to do this simulation of a robot and a CNC on a PC, so we can do a lot of this prove out and concept ahead of time and know exactly what we're going to get from an interface between a CNC and a robot. About any industry you can think of, we're involved in with robotics. A little review of the benefits here. So just in closing, I just wanted to add one more little thing here. Through the use, if we look at increasing productivity, there are additional processes that can be taken advantage of with the robot. When there's long process times, we talked about using a robot to service multiple processes and multiple machines. Within the robot cell, the robot can also add in other pre- and post-process operations such as clearing chips, part marking, deburring and cleaning and washing, add some gauging or inspecting functions, and even some light assembly, labeling, and packing, all within the same cell that can be tending a machine. And lastly, utilizing a robot cell for the management and incorporation of work pieces on pallets, like the SCHUNK VERO-s. So I'm going to turn it over to Brad now to talk to you a little bit about the SCHUNK VERO-s. Thank you.
Good afternoon. I'd like to talk to you a little bit about the next step in the automated machine tending. As you look at this so far, you can see FANUC functions as the brain and the arm of the machine tending. That it is able to interface with the machine PLC and reaches and places things in and out of the machine. SCHUNK steps in as the hand and the experience of machine tending. That is the actual interface between the robot and the fixture, or the robot fixture and the machine table. With the fixturing, and precise fixturing, it provides the experience that an operator, a setup person, can do in the machine. One of the main reasons, or another reason for automated machine tending, is as of this year, the average age of a machinist in the United States is 53 years old. For the next 15 years, the need for machinists is going to be at a premium. Therefore, manufacturing needs to look at other ways to fill the void and allow the skilled machinists they have to supervise and operate larger areas, larger cells. A little bit about SCHUNK. SCHUNK is the world leader in gripping and clamping technologies. Just a few of the items that SCHUNK has to offer. SCHUNK provides lathe chucks for the turning industry, tool holders in the machining industry, chuck jaws for the lathe chucks, stationary work holding, which is a broad selection of different types of work holding, including quick change palleting, pneumatic hydraulic vices, manual vices, vacuum systems, as well as magnetic technology. Those fall under the tooling work holding category. SCHUNK also is the world's largest robotic gripper manufacturer, providing gripping modules, rotary modules, linear modules, robotic accessories, modular assemblies, and mobile ribbing systems. What we're going to talk about today is primarily two areas: the VERO-s, NSE system, NSL palleting systems, and Tandem vicing. The VERO-s system is a quick change system. SCHUNK brings a unique approach to the work holding. To truly enhance productivity, work holding must incorporate at least one of the 5 following categories we have listed: improved setup time, improved table capacity, improved part access, improved flexibility, and improved part quality. However, more than one of those is going to increase your benefits. So we look at these categories combined with other automated machine tending. The customer will then achieve the maximum in the productivity. The VERO-s system has 2 components. The VERO-s is a quick change palleting system designed to change out a fixture within 5 microns repeatable. It is the interface between the machine fixture and machine table. The NSR is designed as a quick change system, which is the interface between the robot and the fixture. The robot would then pull a fixture from a palleting pool, a bookcase, shelving unit, and loaded in and out of the machine using the VERO-s system. Again, with a repeatability of 5 microns or 2/10. The VERO-s system is a fail-safe system in that it functions on a spring clamp methodology, air release. So no air is required to maintain the clamping technology. VERO-s, when the user loads the fixture in, they can go from a different fixture. They can manually load it or robotically load it within minutes without need for indicating it in. As Jeff had mentioned earlier, with some of the side load and other types of robotic tending, the robot can be set up to run evenings, changing out fixtures and parts. Step out of the way and allow the operator to go back in and manually change in standard fixture or even a standard vise in and out of the machine during a day operation. With the VERO-s system repeatability, it allows the robot or the operator to load the machine with confidence and running the program. When a shop sets up a VERO-s system on a standard from machine to machine, it allows a fixture to be set up in one machine and moved to another machine with the same repeatability and accuracy. It also allows for a robot to tend multiple machines using the same fixturing. VERO-s provides the single interface into the machine table. While using hydraulic, pneumatic, or vacuum fixtures, an interface can be provided in the system, into the table, that will eliminate the need for external plumbing, fittings, couplings. So as a pallet is loaded onto a machine, the coupling is made automatically and allows the hydraulic, pneumatic, or vacuum to be connected immediately into the fixture. This automatic connection eliminates the need and the issue as far as external hoses and clamps. The NSR, as you mentioned, is an interface between the robot and the pallet. Again, using the same spring clamp air release technology, the VERO-s NSR will attach to the robot and interface with multiple pallets, multiple fixtures. The pallet that is used can be either made specifically for this, or a PKL interface can be added to an existing pallet in the facility. So no special fixturing is needed. The Tandem vise line is a compact vise line. This is one of the items which we utilize to increase table density and capacity. The Tandem vise is compact, self-centering, precision accurate, can be pneumatically or hydraulically actuated, can be PLC controlled, provide jaw feedback, positional feedback, and provide parts presence. It's available in 4 sizes from 2 inches square to 10 inches square. On the pallet you see in the bottom right corner, a pallet of 16 by 24 enables you to put 24 4-inch vices on one pallet for increased table density. When combined with the VERO-s integrated plumbing, this pallet can be loaded on and off the machine and changed out for various size vices or more traditional manual fixturing. As you see in the picture on the left, the VERO-s system clamps using clamping pins. The pins are placed underneath the fixture or conventional vise, which allows greater table capacity or accessibility. There's no need for external clamps, which allows multiple fixtures to be placed onto a table. As you look to the right, you'll see a row of Tandem vices that is being loaded via robot using gripper technology. These vices can be set up to run multiple products, and for long run times, then the pallet can be then removed using the NSR PKL, and a variety of other vices or other fixturing can be placed back in, and allowing the robot grippers to actually load the parts. The picture you see now is another example of increased density. With the compact vise system, tandem vise system, multiple parts can be combined into a very small area, which allows the machine to run longer unattended. One of the main focuses as you look at automating cells is to allow the machine to run longer unattended, keeping the spindle turning and the doors closed. Another focus in automated machine tending and keeping the machine spindle running is to improve part access. This method of improving part access also improves part quality, in that when a part can be accessed in 5 faces, it can reduce the number of setups, and the precision location, datum locations, can be used for more than 2 or 3 faces. In addition, as you see in that picture, you're able to see on a 5-axis mill 4 individual parts clamped. Often you'll see 1 or 2 parts in a 5-axis mill, which again cuts down the length the doors are closed. By adding 2 to 4 parts, you can increase the door closure time and the cycle run time by 2 to 3 times. Regarding flexibility, the VERO-s system is a complete flexible system in that it can be integrated to hold any type of work holding, whether it be manual, pneumatic, hydraulic. It can be used for vises, clamps, manual fixturing. It can be utilized to hold custom fixturing. The pins can be mounted to a standard pallet or into any existing or current fixturing that a facility has. So no special fixturing needs to be added or created or purchased. The VERO-s pins cost about $100 a piece. You have 3 types of pins, an A, a B, and a C. Your A pin is your primary locating pin. Your B pin is more of your diamond and gives your axial location. If it requires more than 2 pins, all the remaining pins would be what are considered C pins, which are strictly for clamping and pull-down force. And as you look at the last and most important part, no matter if we can have great access to a part, we can increase the density, we can load it on quickly. If we aren't able to do it accurately with precision, all we're doing is making scrap fast. The VERO-s system, work holding pallet system, provides clamping within 5 microns or 2/10, which enables to provide a quality part or product. The SCHUNK work holding is designed to work with the machines and controls to provide a seamless process to enhance productivity and flexibility in the machining cell. Combined with a robotic interface, a robot can load pallets or parts in and out of the machine quickly, accurately, to allow a machine to run longer unattended. At this point, we'll begin to accept questions. You can put them in the chat box, and we'll be happy. Jeff and I will be happy to answer them for you.
All right, thanks. Hey, Brad, can you real quick explain the ABC clamping pins again?
Certainly. The VERO-s pin uses a technology of a clamping slide. The clamping slide goes around the base knob of a pin. It kind of looks like a pull stud in a tool holder. The A pin is a precision pin, which will provide your primary datum location of your fixture. If you need a secondary pin, the B pin is a diamond pin, which will provide you your axial location as your reference datum to your A pin. Beyond that, if there are more pins required, then they use a simple C pin. The C pin is undersized and strictly is used for clamping and clamping force.
Like in a case where you showed 4 of the VERO-s bases, one of those would be an A, one would likely be a B, and then the other 2 are going to be C pins. Correct. And you'll put your B pin the furthest from your A pin to give you your highest precision. Okay. Can you talk about how this system works with existing fixtures?
So in existing fixtures, it's simply a matter of modifying the bottom of the fixture to place your VERO-s pin into the fixture. If you have a pneumatic or hydraulic fixture, it's a matter of adding into it some coupling nipples that would go under the fixture to pass the pneumatics or hydraulics through the fixture. For manual fixtures, even more simple, simply by placing the VERO-s pins under the fixture to clamp on the VERO-s. Once you've installed the VERO-s pins into the fixture, you would load the fixture in, find your reference datum, say on a fixed jaw vise. You would scan that jaw, and that jaw would be stored in the PLC for its home position.
Okay. And you had described earlier that you don't have to be connected to shop air when it's in the machine, since the default position of that spring is when air is attached, the spring allows the fixture to be removed. When the air is off, the fixture is clamped. Is that correct?
Correct.
Okay. Can you talk about any other keys to a successful machine interface?
Well, because of the simplicity of the open and close, again, the PLC can send signals to the VERO-s system through air to open to allow a robot to simply pull a vise or a fixture in and out of the machine. So it's not very difficult to interface that to a automated tended cell.
Okay. Can you talk about the shop-hardened aspect of these systems? I mean, we're in an environment that's got chips and coolant. What's going on inside the VERO-s?
The VERO-s system is a upgraded system from SCHUNK, introduced a few years ago, that is made from a proprietary stainless steel, 55 to 56 Rockwell. It's a hardened stainless steel. It is fully sealed, so it is protected against coolant, ingress, swarf, sludge. It can actually operate underwater without any passing of bubbles. So it's a fully sealed system. The clamping slides utilize a clamp face technology as opposed to some of the older style ball cage technology, which tends to gum up when it gets connected with sludge, swarf from a grinding or machining environment. So it makes it much easier to clean and maintain, and being fully sealed, it prevents premature failure. Great,
thanks, Brad. Hey, Jeff, robots scare people. What type of training is needed in order to be able to operate a robot system?
In many cases, training can be performed on a system on site for operational type training, so it's no different than starting and stopping a machine tool. Those type of things. If the ability to add additional programs is desirable, there are lots of training. We have training classes available, but adding that type of thing is no different than making changes to a CNC program. If you have qualified CNC programmers, they can easily adapt to being able to modify robot programs. Maybe not writing the whole code from scratch, but definitely starting, making modifications, reteaching points, making fine adjustments. Those things can be, there's a lot of correlation between the type of CNC programmers and operators and what can be done with a robot.
Okay. And where do people start? If you want to begin the process of evaluating my needs for automation, where do I start?
Start by identifying the parts and the need for the automation. What are the type of cycle times? What kind of work holding you're going to have? Those kind of things up front. Understanding those pieces and providing those along to whoever you're going to talk to about actually implementation. So we start a lot of times with what we call a plant audit. We'll come in, the customer has some of that information available. We ask some questions to help drive for the information we need, and then we can turn around and at that point bring in a qualified integrator or machine tool builder that has integration capabilities. And as long as they have all of the information up front, It's very easily adapted and quoted or a system developed, and we have great simulation tools. So a lot of times we can up front build a robot cell in what we call the virtual world in simulation, and demonstrate and show the ability to hit certain cycle times or reach certain processes, or develop post processes and other things that we want to add in, and show that all can be done within the necessarily takt time or cycle time of the process.
Wow, outstanding. Outstanding. Hey, if there are people on your team that could benefit from today's webinar, they'll be able to access it from the NTMA website in the coming weeks. I want to extend a big thank you to Jeff and Brad for providing today's informative webinar. In the spirit of continuous improvement, the tech team would appreciate your feedback on today's webinar, as well as receiving recommendations for future webinar topics. Thank you very much for joining us, and have a great afternoon. Thanks again, Jeff and Brad.
Thank you.
Thank you very much.